You're ready. Okay,
Ready
so
when you are.
welcome everybody to the first seminar on formal verification this year. We are fortunate to have Everett. I've known Everett for some years now. I don't actually remember where we met. Everett is the CTO of Runtime Verification. He's been actually in this space for long. He did his undergrad in physics, and then started graduate in Urbana-Champaign in CS. He's an expert in proof assistant in the runtime, basically the K tool, but also work on other tools. He's been involved with many of the key projects in the Ethereum and also with the Ethereum Foundation. Been working on a fantastic project like Uniswap and others, Maker. And we love to hear what he has today on the KVM. He also has dogs, which I love dogs. And he's a mountain biker, for what I can tell. And also a dancer, I think, right? A dancer, like a fantastic dancer.
I don't know about fantastic, but I try.
Okay, yeah, I don't know more. Thank you. Go for it.
Okay. Well, today we're going to be talking about dancing. No, just kidding, but that would be fun. Yeah, so thanks for the introduction. For 5 years now. And when I joined, we were pretty small, but now we're bigger, which is cool, but also a lot of work. And today I'm going to be talking about solidity verification using KVM. I mean, that's really what we're going to get to at the end, but I'm going to focus more on building up background knowledge on K for you guys initially. And then if you want to have a more in-depth presentation on the uses, we can do that later. But I figure kind of that background knowledge is important to understand how our technology works. Yeah, so overview of the presentation, what's K, what's KVM, and then I'm going to show like kind of a cool KVM opcode summary thing, which is which the reason I want to show this is to kind of demonstrate the technology, the underlying technology that we're using. I think it kind of helps to understand better what the underlying technology is. And then I'm going to talk about our KVM Foundry integration. And there I'm going to be focused on some simple examples, mostly just showing how to read the output of the tool or how to interpret the output of the tool on some very simple examples. And then questions at the end. But feel free to stop me with questions throughout the whole thing. I don't mind being interrupted to discuss anything that you want in depth. Yeah, so we're going to start out with what's K. So K is an operational semantics framework. So if you had a programming languages course in undergraduate or grad school, that might sound familiar. But what that means is that you specify in the K modeling language your system or your language. So it's not limited to just programming languages. You could specify your networking system or system of actors or something like that. People have defined all sorts of different like networking, like software defined networking languages, for example, in K, and then done simulations using the K model checker of those. And then the idea is that the K compiler derives the formal methods tools that you would want from your system description. So it's kind of similar to how a lot of people think of a model checker, but not really just a software model checker like what CVMC gives you for C, but more just like a system model checker. But the systems it's tuned for are programming languages. So that's really what we focused on engineering it to be good at, basically. The underlying formalism that makes all of this sound is matching logic. So you have to have, some reason that your reasoning is sound. And we use matching logic as that. Matching logic is a first order logic. And there's various extensions of matching logic that give you fixed points and stuff like that. But there's a bunch of papers about how you can do, LTL or CTL or whatever dynamic temporal model checking you want to do in matching logic with fixed points, basically. And it subsumes a bunch of other logics in the same way that like a Turing complete language is Turing complete. So that I don't know if that's a super interesting result, as it just shows that it's a powerful enough logic, if that makes sense. But in particular, it's a slight generalization of Hoare logic, which in my opinion, it's a little bit more natural of a logic than Hoare logic is. And it gives you a very nice reachability logic prover, and separation logic is pretty easy to encode in matching logic. So it's a bunch of different papers with all these results basically. And I think there's even a diagram on this page, or maybe it's one of these papers or something. There's a diagram showing. No, okay, you have to look through it for yourself. But there's a diagram showing how you can map via conservative extensions or other mappings all these logics into matching logic, and that's fine. Anyway, so every single thing that the K does, right, our interpreter, our prover, our symbolic execution, can be mapped to deduction and matching logic, basically. So we can have proof objects is the nice thing. And the other thing that's nice about matching logic is that the model theory associated with matching logic is pretty simple because it's a first order logic. So it's not like some, complicated like homotopies or something like that. It's just sets, functions, and power sets. And that's all the mathematical background you need to understand matching logic's model theory. So not sure if you guys are into model theory and proof theory and those types of things, but that's, I think, a good reason to use matching logic. Okay, tooling wise, when you give a K specification, there's really two main backends that you get out of that. And there's actually several more backends, but these are the two heavily used ones. There's the LLVM backend, which is really the concrete execution backend, which is where we from your operational semantics extract an interpreter for your programming language or your system. So you can do simulation with that, or you can just use it as an actual interpreter for your for execution. So for example, we have a tool called Firefly, which we don't really work on anymore. Let me see if I can remember the URL. And this was basically where we took KVM, which is the K semantics of the Ethereum virtual machine, and wrapped it in basically some shim code that turned it into a full client. And that full client is conformant with other full clients on the network. So you could actually, resolve blocks and do normal testing stuff like you would with Truffle or something like that. But, Truffle is not as in fashion anymore. And we had this nice coverage thing going on with that. But that was just using the interpreter that you get extracted from the definition. And this interpreter, we really focus on it being performant. So right now, the default interpreter you get with KVM, for example, is on the order of performance as like PyEVM or Ethereum JSVM, so other interpreted languages interpreter. And we have a certain optimization that we haven't really released yet that puts it more on the order of the compiled clients like CPP Ethereum, which I think is called EVM1 now, and Geth, for example. So we really focus on this interpreter that we get being a performant interpreter, and that's because some of our engagements use the C semantics, and there we need to be able to execute full C test suites, in a reasonable amount of time. Not obviously orders of magnitude slower than GCC, but still it needs to be done in a reasonable amount of time. And the Haskell backend is for symbolic execution. And so this, you can, start to put symbolic variables in and make queries about those symbolic execution paths that you get out of it. So yeah, most of our tools are powered by K. If you go to our website, there's a couple on our products page, there's a couple tools listed. Most of them are in the blockchain space, but then there's the ones that are in the embedded system space too, like RV Match and RV Monitor. And then if you want to learn more about K itself, you can go to kframework.org, and there's a bunch of resources here, including like a Discord server you can join that will answer any questions you have. And we have various editor support like syntax highlighting and stuff that you can install as well. Okay, so that's overview of K. Just briefly, what's the problem that K is trying to solve? It's this problem here. If you've seen any of my other presentations, you've probably seen this diagram. But you have a bunch of programming languages and a bunch of different tools that you want for those programming languages, and then each, this arrow here from C to model checker is CBMC, and then from Ethereum VM to deductive verifier, symbolic execution, I'm not sure what you guys prefer to call it, would be, Certora. And there's a bunch, every one of these languages has its own tools for doing these various tasks. And so this is obviously a lot of repeated effort, which means more opportunity for bugs and and kind of wasted developer time. So this is kind of how K tries to solve it. And there's other tools trying the same thing. I think actually one of the presentations I saw, you guys are trying to also have like other languages mapped to TAC, for example. So that is more like the boogie approach to this problem, which is, have some IR that you map the high level language into, and then do the verification at the IR, and then map the results back to the source language. Apologies if I totally butchered how your guys' tech works, but that's my understanding at least. And so we don't really do the IR thing, right? Like we have a direct representation of the language in question in K, and then we do the reasoning directly over the K itself, which has drawbacks and it has benefits. The drawbacks being that, you can make it so that you have a very performant verification IR that you're encoding into. But the benefit is that you don't have to do any mapping of the results back to the source language or anything like that. So, the other benefit, I guess, is that you get like debuggers and stuff like that for free, which isn't listed here, but we do have like symbolic debuggers. Okay, any questions about, oh, I have another slide about K. So just some example K languages. This is the K programming languages tutorial. This was really the original reason that K was developed, was to teach the programming languages course at UIUC. And this was years and years ago. And so there's a bunch of sample languages here, including like some functional languages, some imperative languages, some, function language with algebraic data types, imperative language with multi-threading, how to make type theories in K, because you can actually make a typing semantics as an operational semantics, and then your execution semantics as an operational semantics, and you can do a proof of type preservation via like a mutual confluence proof between the two semantics, which is kind of cool. And some other languages here. And then if you go into the second one, these are more real languages. So simple is like an imperative, multi-threaded, C-light style language. Cool is, I think, a similar. I can't remember actually what cool is. Fun is like a functional language with like algebraic data types and partial application and closures and stuff like that. So it's like feels like a Haskell light or a Lisp light like language. And then logic is like a Prolog-esque style language. So it's a declarative logical language where unification is the main driver of execution, and you have some sort of search for proofs in the language, basically. So this was the main reason that K was developed initially, was for this teaching of programming languages to undergraduate students and to graduate students. More recently, starting in 2018, we started to, do commercial verification using K. But that was only after, there was several years of academic work on building up a prover and building up the theory and all that stuff, because K was engineered at first, just for the concrete execution aspects. So here's a list of kind of K active projects. This is missing a few, unfortunately, but it'll be updated soon enough. One that I think is kind of fun is this Deducti project. If you guys are if you guys don't know what Deducti is, but it's basically it's trying to be like the LLVM of interactive theorem provers, or the LVM of theorem provers in general. And so it has Deducti, like a Deducti definition can be mapped into a Coq definition or into an Isabelle definition, or also a Coq definition can be mapped into a Deducti definition. So you can kind of map between the different theorem provers via Deducti, and they have their own proofs about how all of this is sound and stuff. So that's its own project. But a student at INRIA just started making a deductee backend for K, which is kind of cool because that means that now you can use that to, for example, map KVM or our WebAssembly semantics or, Yele or Michelson, any of the semantics we have here that they're listing here into the Coq theorem prover, for example, and do your proofs in Coq instead of using the K theorem prover for it, which is kind of cool. And as far as I know, these three languages up here, like WebAssembly, EVM, and Michelson, are the ones that is working for. It looks like also P4, which is a software-defined networking language for defining like network topology and how packets should be routed throughout a network, is also working or something. So Amelie is kind of actively working on this project. So I think that's kind of a cool project. And then there's a bunch of semantics themselves, which are the large ones. The biggest one that we're using currently is obviously this KVM and the KCC. And then one that's a couple that aren't listed here are KPlutus, which we also use to do verification of Plutus smart contracts, and KAVM, which is for the Algorand virtual machine that we use to do verification there. Obviously, in those languages that don't have, as much tooling already available for the language, K has that competitive advantage of being able to much more quickly have at least the initial tooling available. And then you can also just, that was kind of an incomplete list, but you can just go here and do a search for semantics in our repositories and get kind of a list of all the different things. You probably will notice a lot of like blockchain specific things going on here. Semantics.
Do you prefer to have question in the middle or after?
Anytime, yeah. What questions do you have?
So it's a more like a high level question. Like I've been in this space, as you know, for long. So the killer application for proof assistant, usually there are two things: is the compilers like the ComCert and the operating system. So it sounds like when I look into the K, I don't see, or am I wrong? Like, do you see what I'm saying? Like
Yeah.
I have done the cell for. So why is it that because it's the tool was not appropriate, or just there was no interest, or do you know? I mean, all this. So is my question clear? Sort of.
Yeah.
Ask people in programming language, they will tell you this is the most interesting application.
Well, I mean, I don't know. Like people pay us to do things and then we do them, right? I mean, honestly, for a lot of the blockchain languages, people have been interested in a lot of the non-verification tooling that we have too. So we have like a default debugger that you get for your programming language, just using our interpreter, for example, and it's got like a nice visual user interface, and you can step and set breakpoints and stuff like that. That's something that people who are making their own programming languages for their blockchain have been interested in, just because otherwise they have to go and build up all that tooling themselves. So even just normal developing tooling or measuring coverage, for example, like coverage of test suites, something that sounds pretty simple if you're talking about EVM or Solidity, because that tooling already exists. But for a new blockchain, new programming language, none of that tooling exists already, right? So it's nice to just have, okay, it takes about the same amount of time to define the K semantics as it does to define a Python interpreter, and you get the debugger for free, and you can also reach and start to do verification with a little bit of work, but also basically for free in comparison. So for, like I was saying, for nascent programming languages, there's obviously a pretty big competitive advantage there. Now on the more advanced tooling side, yeah, we do have a project to make basically basically a compiler, like a verified compiler for your programming language. But that's a little more experimental, and I'm going to be talking about something kind of related to that here, but not that full project. So I don't know if that helps.
So you're saying that you're basically building something like an IDE. You have some kind of, that's interesting. Okay, thank you.
Yeah, and I mean the thing, like, you can, when you're building up an IDE, you can either focus on the most advanced tooling. Like if we were to try to break into the Java market, no one cares about having another Java debugger, right? Like, so that would not work, right? It would have to be something very advanced. That's going to take a lot more work. But if you're talking about like AVM, like the Algorand virtual machine, there's hardly any tooling for that, right? And so even just the simple debugger, the test coverage measurement, the property testing harnesses, stuff like that, that you get for free from a K definition, become a big step forward for that ecosystem, right?
Makes sense.
Another maybe quick question. It looks like you've developed semantics for a lot of the underlying virtual machines. I was wondering if you've considered, or why you didn't produce semantics for higher level languages like Solidity or Move or things like that.
Yeah.
Or whether, or if you've considered that.
There were 2 projects to make Solidity semantics. They were academic, and we were just advising those projects, and they didn't really have the rigorous development model needed to see them through. But I mean, honestly, the big reason is that developing semantics for the VMs is easier. That's the first reason. It's faster, and a lot of tooling already exists to map the results back to the high level language if you have the output of the Solidity compiler handy. So that's one reason. And then I don't know, it's just the other reason is more, I guess, philosophical or something, which is just you want to verify the code that's actually being put on the blockchain, right? Like you want to verify the EVM bytecode, not the Solidity code, because then there could be, some mismatch in the semantics of your semantics of Solidity versus what the Solidity compiler considers the semantics of Solidity, right? So that's kind of the other reason. But I mean, that doesn't mean that it's not a good idea. It still could be a good idea to have a Solidity semantics, because doing verification in that semantics might be a lot faster than doing it at the EVM level, and then you just check it with your EVM verifier too. So I don't know, like time
And it also,
and
like the additional tooling is something that would be useful. Having a good Solidity debugger and a good Solidity, the other tooling I think would also be useful. But
yeah,
that's
actually,
cool.
that's a good point. I didn't think of that.
Thanks.
Yeah. Any other questions about K? Okay. So that's the K portion of the presentation. And then I'm going to talk a little bit about KVM. So we have this domain that we bought, kind of thought it was funny, called jellopaper.org. But this is basically just a direct mirror of this EVM semantics, is published automatically on CI, which is this repository here. And yeah, I mean, one of the big things for us is that we care about having full, complete models of the programming languages, right? We don't make any simplifying assumptions about the languages. So we model gas fully, we model, I don't know, the way that transactions are processed fully. We have like the RLP decoding process built into the semantics, like everything that you need to run the conformance tests as a full client is built into the semantics, right? So that's I think something different than a lot of the other tools that are making kind of simplifying assumptions about the languages that they're doing verification with. Even something like CompCert is making simplifying assumptions about the C that's coming in to the tool, for example. So but this just gives you, because we can run conformance test suites and we emphasize having an interpreter that's fast enough to do that in a reasonable amount of time, this gives you higher confidence that your verification results actually mean something. Of course, that added detail is, it comes with a cost, a performance cost, right? But that's okay. And then, so here's an example proof when we're talking about the reachability prover, or I guess this is a specification, and then when you run it, it becomes a proof. But I'm just going to read it for you here briefly, but don't have to spend too long on it. And here's it's a claim, so it's something that is a proof obligation. It's not assumed as true yet. And here on the K cell, we're saying, begin execution goes to halt. So this I read as goes to, and this is the reachability, the all path reachability arrow. And so what that means is, on all paths, if I start and execute, I will end in halt, right? Given the other conditions that are present in the proof as well. And for example, on the output cell, which is when you do like a return in EVM or in Solidity, you do a return. This is what gets populated in KVM. on all paths, no matter what the output cell started as, I will end in a 32-byte buffer that just has the number 1, so just true. So this is a transfer, and so it's supposed to return true if the transfer goes through. And once again, on all paths, no matter what the status code was before, I will end in success, as opposed to like revert or out of gas or Stack Overflow or underflow or all the other ways that it can revert. But here on the call stack cell, for example, I'm asserting I start with some call stack cell, I'm at some call depth, and I end with the same call stack cell, right? So that means that, it's not like I'm nested somewhere deeper and I hit the end of execution and then I get that true value. It means I have to be at this call frame, I'm getting the true value. So that's to, prevent some trickery with that. Here's your program, which is, some bytecode from some Solidity. And we pre-compute the valid jump desk, so that's why that has to be duplicated here. And then, here we're just saying, okay, whatever the ABI call data of the transfer function is applied to 2 symbolic arguments like the 2ID and the value. That's what we want to start the call data cell as. So this is a symbolic call data, right? We have the call data from the transaction populated into this cell. That's what these XML like tags are called, as cells. You can think of it as like a record in another programming language. But we're starting with a symbolic call to the transfer function where the 2 arguments are symbolic. Word stack starts as a valid empty word stack. Memory starts as a valid empty memory. And we don't care about their final states because that's thrown away when you go up to the next call frame anyway. Program counter starts at 0, right? Then there's a bunch of other don't care transitions, which are, underbar goes to question mark underbar. And then we have like the accounts storage. And so the balance doesn't change. The account ID is the same. And then the storage in the balance. Okay, now we're seeing the actual effect that we're expecting here, right? This is the storage of that account. We're seeing of the ERC20 token account that we're talking about here. So we have some hashing scheme for the Solidity locations. So we tell it, okay, we're using the Solidity hashing scheme instead of the Viper one, or there's a third hashing scheme we have present as well. And the balance of the from account goes to the balance of the from account minus the value, and the balance of the to account goes to the balance of the to plus the value. And then as part of the preconditions of the proof, we have these requires clause. And so a bunch of validity conditions on the various variables that are showing up in the specification, right? So like the account ID is in the correct range, the caller ID is in the correct range, origin ID, these are all just validity conditions on the initial spec. And then there's the actual specification preconditions, which is, here in this particular spec, we're saying the caller ID and the to ID are different, right? And that's key because here we're saying that they populate the caller ID and the to ID populate different entries in the balances map. And so if they were the same, this wouldn't even be a valid map at that point because you'd have 2, entries with the same key. And then the value is less than the balance from, and there's not an overflow on the calculation of the balance to. And stopped is not true, so it's not paused. So, and then a bunch of things about keys not colliding in the storage, because this hash location thing, all it knows is that it's a function. It doesn't know anything else about it. So, so this is a case specification. Any questions about that, or?
Is it possible in this language to add to this specification and say that no other balance changes?
Yeah, actually that is specified here, because see this underbar map, which is the rest of the map, right? It's which includes the rest of the balances, but it also includes other variables defined in the Solidity code. It says it doesn't change, right? It just says underbar stays as underbar. It says only these particular values change.
I see. Cool. Thank you.
But you could omit that. You could change this to, if you wanted a weaker specification, you could say underbar map goes to question mark underbar map here in parentheses, and that would say this change happens and the rest of it changes however you want. Okay, so, but this, that like writing those by hand, like no way, right? Like and that was like one case of one function, so no way you do that. So any real verification project is using some sort of DSL. This was one that was developed a while ago by the DAP Hub for the maker verification. I'll just show you a quick example what that looks like. And here they have this language called ACT that they developed, and it's actually still maintained. At this repository here. This is the ACT language repository. And so ACT is this specification language that has backends to different theorem provers, including a K backend, a COC backend, and some SMT backend or something as well. So you can write your specification and then get the needed definitions in your theorem prover of choice. But it's Ethereum specific at the moment. So, but anyway, this is what a behavior looks like. And let's see if we can find like a more interesting behavior. You guys are probably familiar with Maker's multi-collateral die system, I imagine. And so here, this is, this looks a lot like the K that you would get, but the rest of it is more compact. And I think the modern ACT even has more compact specification. But this ends up, generating for each of these if and only ifs 2 K specifications. So that's 2 specifications, 4 specifications, 8 specifications, and then these are just preconditions. And so this one ACT specification is going to generate 8 K specifications of different code paths, and then use the K reachability prover to verify that. And that's actually what the proof I was showing you before was generated from an ACT specification. And so this particular specification of multi-collateral die is generating something like 1100 K specifications that cover all the different functional correctness behaviors. Okay, so that's KVM. And then I wanted to, running very low on time. I wanted to quickly go over this opcode execution thing, but I'll do that super quick, and then we'll see if we can get to the Foundry integration stuff.
You can run a bit. We are not so strict.
Okay, sounds good. So in the KVM, this is the actual what the specification of the EVM semantics looks like here, and it's all driven by this sharp execute thing, which is in sort K items. We don't have to worry about that too much. But basically, what's happening is, if execute is the next thing to do, and here I can see it's the next thing to do because I'm looking at the left of this rewrite arrow, and I have a dot here, which is the unit of the associative operator here. So actually, execute is the 0th element on the K cell, and that's probably not very clear, but I can explain it better if you guys would like. But if execute is the next thing to do, then insert ahead of the execute something where you're looking up the next opcode to execute from the current program. So the program is byte indexed. You grab the current opcode from it, and then the disassembly schedule, so it'd be like London or Istanbul or whatever the disassembly schedule is, because it changes the way some of the bytes are interpreted for disassembling, right? And then when we have looked up that opcode, we could have a miss that the opcode lookup fails, and that could be because we ran out of program to execute, or it could be because because not a valid opcode, that program counter. But if it's a hit, right, then we go into this kind of pipeline architecture where first this follows by. So this means first we're going to do this, and then we're going to do this, and then we're going to do this, right? And so first we're checking if this is an address operation. And so there's a couple, like if you get the balance of an account, or if you get not the balance of an account, if you get like the ext code size, or you do like a call into another account, some of the arguments are going to be interpreted as addresses. And so we need to wrap them modulo 2 to the 160. And so that's what this line is going to do here. And then we go into actually executing the opcode. And then we increment the program count to the appropriate amount, which is usually just 1. But for the push opcode, it could be 1 plus the width of the push. This execute thing folds out into like another 8 steps. You can see here, this all only happens, this transition in the transition system only happens if there's not going to be a stack underflow or a stack overflow for that opcode, and we're not going to have a static mode violation, right? So that would be, if the static flag is set and it's an opcode that changes state, then this rule will not fire, and then one of these rules will fire, right? So if we have a stack underflow, then we're going to go to this halt state. If we have a stack overflow, we'll go to this halt state or this error state. And if we have a static mode violation, then we go to this static mode violation state. The execution itself, well, the first thing we do is we look at, is it a unary stack operation? If so, go and grab from the word stack, the first item on the word stack, and replace the word stack without that first item. And if it's binary, grab the first two items now. So we just do the argument lookup. And then once we have the argument lookup, then we have the gas computation. So we say here, okay, once you get the arguments, compute the gas of the opcode and check that there's enough gas. And if there's not enough gas, then do the revert. And so we have a big table here of, okay, this is the gas it takes to do an S store, and this is the gas, some other rule for gas of S store, exponentiation, call data. So a big table of all the gas calculations, which is all schedule dependent, for example. And then if the gas calculation goes through, you deduct the gas, all that, then you actually have the effect of the opcode, which looks something like this, right? So you have like add, and we've already done the argument lookup, so it has its two arguments. And so we do the word addition, which is just integer addition that wraps around. And then we push that result onto the word stack, right? So that word addition, I just want to show real quick what that looks like, because it might be useful for understanding the demo later. It's just, it's just integer addition lifted through this chop function, right? So word addition is a total function on integers, and you do the normal integer addition, but then you apply this chop function to the result. And the chop function is kind of it's iconic, it's so used so much. If I can find it. Oh, it might be in word.md. Yeah. So chop is just, positive modulus of 2 to the 256, right? It's positive modulus specifically. So there's two different modulus operators you could use where one of them will potentially return a negative value. This one always returns a positive value. Okay, so anyway, that's kind of, the whole point of all this is that one opcode executing takes like on the order of 10 to 15K symbolic execution steps, or K operational semantic steps, right? And this is nice for having like a modular definition, similar to how the yellow paper is modular, right? You have like a table that tells you, this is the effect on the stack, this is the effect on the gas, this, it's all modular in that way, but it's bad for performance, right? And so a kind of cool solution or cool application here is we can build these specifications, which are doing that same operation in one shot, all 10 steps in one shot, instead of, it's like a bigger step in this small step semantics, right? And so you do this, this next operator on push n, and it has the effect on the word stack, on the program counter, on the gas, all in one place, right? This is obviously less compact than the original specification and less modular as well. But it's more performant because you're reducing 10K steps to 1K step, right? It's just fewer rewrite steps you have to take. And then we put this priority 40 flag here saying, prioritize this rule over the original rule in the semantics, because the default priority is 50. But we don't want to just put these in and trust them, because they're not going to be used in the conformance checking and stuff like that, right? So we need to verify them, and that's actually checked on CI every time. And so if the semantics of any of these opcodes changes, then these summaries have to change of their behavior, which is annoying. So instead of doing that, so we verify it's an all path thing. Instead of doing that, we generate those specifications. And here's the results of doing that. So here's some simple specification that I used as just a benchmark for this, calling the approve function on some ERC20. And, you know, it's some, these are old numbers, but it's some, you know, 30% performance improvement if you include these bigger steps in the semantics, and a 20% reduction in the number of K steps that are being taken. Can you guys still hear me? I might have just lost my internet.
No, you're fine.
We can hear you well.
Okay. So we don't want to manually write these. So we have this this library called the pick library, which is kind of like a programmatic API to K. It's open source, and it gives you programmatic access to the symbolic execution and stuff like that, all in Python. And so you can kind of build a K term, throw it at the symbolic execution engine, get the result back, do some mangling of it, throw it back at the symbolic execution engine, build a proof from some of the terms you have and stuff like that. That's what the pick library gets you. And in particular, it's used here in this build spec script, which basically, yeah, I'm not going to go through it in super depth, but it just builds up. It builds up actually a dummy specification that looks kind of like these rules here, but instead of looking exactly like these rules, all it says is next of push n goes to, and then here we put error state. We say we're trying to prove, we're asking the symbolic execution engine prove that next of push n always goes to an error state. And the prover comes back and it says, well, no, that's not true, because sometimes it doesn't error. And here's the counterexample. And the counterexample it gives is exactly the state update of when it doesn't error, right? And so we that's what this file here does, is it builds up those specifications programmatically. Next of, you know, push n, or whatever the opcode it is we're trying to summarize, goes to some error state. And let me see if I can find where it says error state. Although it's been a while since I looked at this. Yeah, I don't see where it is off the top of my head. It gives back the counterexample, and then we just build now a new specification that says next of push n, given the path condition for the counterexample, which it infers because it's doing symbolic execution, goes to the valid update state of push n, right? And so then we build that rule into the semantics as a new thing, and then we ask the all path reachability prover to verify this rule first, and then once it's verified it, okay, now it's safe to inject it back into the semantics as an optimization. So that whole process, instead of manually writing the specifications, is automated. And you know, you only want to keep every extra rule you add to the semantics is overhead. And so I just did a kind of ad hoc timing of a bunch of opcodes based on the frequency that they show up in programs, and I timed basically, okay, if I add the push opcode, is it a performance improvement? If I add the dupe, if I add the swap. And so I found that these 8 opcodes, if you put them in as optimizations to get these bigger steps, you know, give you a performance boost of about that 30%. So that was kind of cool. So, but you asked about compilers earlier. We have another project that pushed this idea even further, to where we would say, don't stop when you hit, you know, don't stop just at a single opcode, stop at a basic block, right? And so it would do symbolic execution until it hits the end of a basic block, and then it would take that final state that you get and build a new K specification that says initial state goes to this final state. It would quickly re-verify it using the all path prover, and then if that verification went through, it injects it into the semantics again as a higher priority rule. And this was a massive, this is like 100x performance improvement. So we're working on making that like a generally available tool for the K semantics, because it's a language independent tool. There's nothing like, we define a basic block in this case, not as you reach a jump or a jump by or a jump dest. We define it as you reach a point where symbolic execution branches, right? And that's a language independent heuristic for basic blocks. And so we are able to have kind of a language independent compiler. We call it a summarizer, but it builds a new K definition. You take your old K definition and your program, and you get a new K definition with these higher priority rules in it, that's 100x faster for your particular program, but for any other program, it falls back to the original semantics. So I don't know if that was clear for you, Muli, but
It is clear. It's very interesting. So it's basically your way to do some kind of performance improvement by. I'm thinking if this is something that a project can use. So it's not for. So who is the target users? Is the Solidity developers? Who's the client?
yeah, I mean we're still kind of figuring that out, but I mean the client for that immediately would be people who are trying to do verification using KVM because it's slow, right? But the performance improvement you get because it's a K, because you take a K definition and a program and you produce a new K definition that is specific to your program. So you take like KVM plus my EVM program, and now you get K my program. You get a specific K definition that's just that program. That K definition, that 100x performance improvement, is both it's all our tools. Our symbolic execution engine has that 100x performance improvement. That's just because basic blocks in EVM usually are on the order of several hundred K steps. And so you're compressing those all into one K step. But it also is our concrete execution engine. And that puts us in the performance realm of normal full clients like Geth and EVM1 and Foundry's full client for our concrete execution. So then suddenly you have this situation where, you know, our compiler, because that's a static, no user intervention required ahead of time pass that you can do on your program. It's expensive. It takes a long time to compute. But once you've computed it, store it, and you can use that as your interpreter. And then at that point, like, is there a reason to have something other than the K semantics for doing interpreting even? Because you can reach the performance of compiled languages with your K semantics. So that, I mean, we're not quite sure, but we're basically thinking of offering that as like a SaaS thing, like where we generate these summaries for you on SaaS, and then we give them to you. You get the summaries, right? And you can validate them yourself, right? Like you can take the summaries, you can run the normal all path reachability prover on the summaries to validate them yourself, but then you just leave them there, and then every operation you do with the K semantics, including verification or just normal execution for our testing coverage metric or debugging for other languages that care about those things, you know, has that performance improvement available to it. So that I don't know if that answered your question.
All is good.
Okay.
Great.
Yeah. So I want to talk quickly about these Foundry property test things, and probably going to just show the output to avoid going over time. But I'm assuming you guys have seen Foundry property tests, but I'm just going to quickly go over what they look like.
But it's okay. Yeah.
Yeah. You have some sort of setup function which does some initialization, and then you have functions that are prefixed with the name test, and they can have arguments associated with them. And Foundry is going to run your setup function, take that state that it gets, save it, and then run all of your test functions in the context of that saved state, basically. But it's going to pick, random arguments to fill in for these parameters here. And it's going to do, a bunch of runs till it can find a counterexample, or until it's convinced that it's done enough runs that it's not. And so we have our own like conformance test suite for our Foundry integration, because it's, for Foundry, you have to have what are called these cheat codes. So anywhere you see these VM dots are what are called cheat codes. And these basically give you, super user access to the VM state or something like that, right? Like you're allowed to make specific types of modifications to the VM state that enable you to, the big problem with in-solidity testing is that you're not having as much access to the overall VM state as you would have in out of solidity testing, right? So this solves that problem, right? It gives you that super user access to the VM state or something. And so we had to implement all of those cheat codes in KVM, which is done here. And basically we, so this file here also is kind of the only documentation of this integration, FYI. But we're going to be fixing. We just interrupt any calls that are into this specific cheat address, and that's exactly what Forge does as well, right? It's interrupting calls into this specific address and then does something else. It interprets them differently, right? So, and that's all defined here. Like if you do warp, which is to affect block timestamps for tests that need to be fiddling with block timestamps, then it just goes to the timestamp cell or that record in the state and just updates it how the warp says to update it, right? So that's something that you can't do with normal EVM opcodes, but you have this cheat code which gets you access to do that. So if you want to have Foundry integration, you have to, this is a prerequisite. You have to have this way of interrupting calls and interpreting them differently for calls into that specific address, the Foundry cheat address, which is pretty easy in an operational semantics framework because we just are able to inject rules that are higher priority than the original semantics, basically. So that's the basics of how the Foundry integration works. And we have a large test suite here that you can kind of peruse that we have just written mostly by hand because we couldn't find a good conformance test suite of all the Foundry cheat codes. And so these are all just a bunch of silly small tests that the various cheat codes are behaving how we expect, and we run them through Forge and we run them through KVM and we make sure that they're getting kind of the same result. So it's just a conformance test suite for the Forge cheat codes. And these Foundry tests can get really big. So here's a client that we worked with to help them on their Foundry journey. And you know, there's each of these files has, you know, a bunch of tests in it, and they even found their own way of encoding invariants. Foundry has a way of encoding invariants as well, but somehow they found that that wasn't quite sufficient for what they wanted, so they made their own way of encoding invariants, which that's fine. Basically, you do like your setup, and then you require your invariant, then you do your test scenario, and then you assert your invariant at the end. So that's kind of how you do your own invariants like that. So yeah, that's the basics of Foundry. And yeah, the benefits, this is what Foundry output looks like. And the benefits here is that you get lots of runs and it's super fast. And another thing that is not as talked about is that you can have kind of like a poor man's monitor out of Foundry because it has this option to fork Mainnet. So you can run your property tests against Mainnet. So if you have some property that you want to monitor on the live network that is expressible as a Foundry property test, you can actually just set up Forge test in a loop, calling it every block, and you know that could be used for all sorts of things. But you know, the most obvious application is just monitoring live network state in some sort of low efficacy way, not like a really, it's not as powerful as something you get from one of the paid services. Okay, so yeah, this is a link to that conformance test suite. And if you want to do any of this, then you need to set up KVM. So the first thing is to install KUp, which is the K package manager. That is the wrong link. Fix that, and then it'll be fixed in the slides for you guys. And so KUp is basically a thin wrapper. All of K is distributed via Nix. We also have like Mac and Ubuntu specific packages and Debian specific packages, but Nix is the easiest way to install it all. And so if you just run this command here, it will first check if you have a Nix installation, and if you do, then it will proceed to install the K Nix caches and stuff like that. But if you don't have a Nix installation, it'll first try to install Nix for you, which will require your sudo access. Anyway, you do that, now you have KUp, and then you can do something like KUp list, and there's, you know, various packages that we distribute. These are our open source projects that we distribute via KUp, and KVM you can see is listed there, Kplutus. And the first time you do KUp install KVM, it's going to take a long time because it's going to download all of the binary caches for K and KVM and core RPC and core exec. It's going to download the binary caches there for the ones it needs for that package. But then the next subsequent times it goes faster. So, and you can do KUp list and you get like an output that looks like this, which is, you know, KUp is up to date and core RPC could be updated. And there's also a way using KUp to build from source most of the projects as well. There's a small repo here that I've just dumped some tests in called the Foundry demo repo. And on the Satora presentation branch, I have some silly tests in there meant for pedagogical reasons. And then, you know, the first thing you do on those tests is you do forge builds. So I have those here. This is in that Foundry demo repo. Yeah, on the Satora presentation branch. And so, you know, you would just do forge build, and I already built it before, and so that already happened. And then you would call this command after you have, so I have KUp list. Every time there's an update, it has to re-download the, I don't know, the caches or something, but there's KVM. Oh, okay. So I could update to a new version of KVM, but don't need to. And that's the version of KVM I have installed currently. And then, so I could do KVM Foundry compile. I've already done that actually. And I added these arguments here because as soon as you get into doing verification of real things, you are going to have to provide lemmas to K that tell it how to do algebraic simplifications of things. So K is mostly like a rewriting based things. When it can't decide if a path condition is feasible, for example, it will first try to apply rewrites that the user supplies in a file called lemmas.k. And then, or, you know, you can name it whatever you want, but then after it's done that, it will encode the path condition to Z3 and ask Z3 if it's feasible. So, but it's much faster to discharge those queries with rewrites than it is to discharge them with Z3 queries in most cases. And it's less opaque too. So very first specification there is this test assert bool failing, and it's just a Foundry property test that just takes a symbolic B as an argument and just asserts that it's true. And this is the incantation you would make to run this particular test. So I'm going to go ahead and do that. I have like a in the repo committed to the committed to it is this script just called do it that you can uncomment just different test lines to see the different examples here and run them and get the output. So I'm going to run that, and it's going to take a while because the because I have the do it script set to like basically do a full clean, full compile, full prove every time. So first it has to, you know, call the forge compilation after it's done the clean, and then it's calling Foundry compile, which is the command that I had prior slide, this one here, which you would really only have to call once for all your specifications once you've written them. But anytime you change the Solidity code, you need to recall that Foundry compile because it generates K, you know, a massive K helper file that is specific to your Solidity code, basically. And after compile runs, which takes a little bit, then it's going to call approver, which is also going to take a little bit. There's like a basically a 2-minute overhead per proof, just regardless of the size or complexity of the proof. So okay, so compile is completed. Now it's calling Foundry prove, a bunch of warnings and stuff, and it's written this file, and now it's written this file. So I'm going to inspect this file right here. This is the generated K specification. And it's similar to what we saw before, right? It's saying, we're starting at executing at the beginning. So if we go and look at the program counter cell, it's going to be 0, and the word stack is going to be the empty word stack. And going to halt, which is the end of execution. And we're calling like this right here. This isn't syntax that's available in EVM. So that Foundry compile step inspects the Solidity generated sources and generates new syntax that gives you this kind of sugar, right? That you can say just, contract name dot function name and apply it to symbolic arguments like that variable B, that was the symbolic argument there, is here, right? And so here we're doing the call data. And then also in addition, for example, the program's been filled in for us and the jump des has been filled in for us and stuff like that. So yeah, not a whole lot of interesting in this specification, honestly, because most of it is boilerplate, and the real work that happens is right here. This is an ensures clause. So I talked about requires clauses before, they're preconditions. Ensures clauses are post conditions. And so here we're just saying that the Foundry success predicate applied to the final state returns true. And I'm not going to go into detail at the moment what the Foundry success predicate is, but it's the same one that Forge uses for determining if tests passed. Basically, we use the same one. And okay, so that's one file that's interesting to look at, but you would look at it once and then never look at it again, because that's, why would you do that? And then there's another file called the debug log, which can be helpful to look at as well when things are going wrong, basically. And so this debug log is a log of all the rules that the symbolic execution has tried to apply in order to discharge your execution. So this can be useful to inspect when things are going wrong, because it can tell you, like if you do a search for this thing, I can see, I'm going to just do this a little faster. I can see, okay, there's 617 selections. So that means that it's taken 617 steps of symbolic execution. Maybe it's failing at the 618th, but I want to inspect the 615th. Okay, so rerun it and tell it only go to 615 steps or something like that. That can be one useful thing. And then also just looking at the rules themselves. This is a source location. And so here it's telling you the rule that I applied here was the one on line 293 of evm.md, and that can be useful as well for knowing where it's getting stuck or having problems. And then here it's saying, I got stuck, like a warn stuck claim state. And so I'm going to go back and look at the output. And the reason I picked this example is to show you guys how to read the output. And so here you have the halt, which is what we expected. If you remember in the specification, we said that all paths should reach the halt. So that's not failing, right? That's doing the right thing. The status code, though, is saying EVMC revert, which means that somehow we hit like a reverting path, and that is a failure condition for Foundry tests. If you hit a reverting path and you didn't explicitly say, I expect to hit a reverting path, that's a failure condition. So the next thing to do is to go down to the side conditions and begin to inspect them. And it's telling us this side condition is the interesting one, and it's telling us, hey, like, B could be 0, right? Like the variable B, the symbolic variable B that went into the test could be 0, right? Which obviously could be, right? Like we're not saying anything about that. And so here I've kind of distilled out that information here as the way to read that. So we fixed this test by just putting if B on the front of that, right? So we only are asserting B if B is true, right? And then the output now says top, which is how to say in matching logic that a proof went through. And then I have several more examples here, which are going to be distributed in the slides. But, here's an example of like a WMUL, which is like the, WAD multiplication. And, here we're trying to test, is WMUL monotonically increasing, right? So is this, does anyone know if this is true? Is WMUL monotonically increasing like this? The answer is that it's not. And I've saved the output so that you guys don't have to sit through the torturous wait of running the tool. And it gives back something that looks like this. And a bunch of other side conditions as well, but this is the interesting one. And I've rewritten this using the name for this number, which is max uint 256, and saying that max uint 256 divided by a, which is that first argument for into the WML, is less than the b. And this is basically, you know, if you move this over, you multiply it over, then you're seeing, oh, okay, a times b is greater than max uint 256 as an overflow condition, right? Okay, so we modify our test to say if b is less than or equal to max int over a, then the test should go through. And now it's giving us, well, a could be 0, and so that's this division could be failing. Could the Solidity compiler is inserting a check that the division is not failing. Okay, if they're both greater than 0, right? And now it's giving back this, which is saying that the calculated C, which is this result right here, which is a times b divided by that WAD scalar, is less than a, which is not what we're asserting here, right? Oh, it's because in WAD arithmetic, anything less than this number is actually less than 1, and so that's decreasing, it's not increasing, right? Okay, so now we modify this condition and not just say that they're greater than 0, but to say that they're greater than 1, and the proof goes through, right? So there we didn't have to provide any hints to K to get the proof to go through, but I wanted to make an example where you do have to provide a hint for whatever reason, and that's this example here. So this is a slightly different property, right? It's like 0 is less than a and b. Assert that the you know, that it's not strictly increasing, but that it's weakly increasing, right? That it's only a little bit increasing. And in the side condition you get from running that proof shows up this condition here, which is saying that, you know, this is saying that a is less than or equal to chop, which remember is that mod 256 operator of the multiplication of the two divided by the scalar. It's an overflow condition, basically. It's saying, like, I don't know if this overflows or not, and so I can't remove the chop, right? Like if this doesn't overflow, the chop just goes away, right? Because it's within the correct range. But if you inspect this other condition here, this one is actually saying that multiplication doesn't overflow. And so for, you know, whatever reason, K cannot infer that. And so you add this lemma here, which says X times Y is less than the max of the chop, which allows that chop to simplify away. So it goes to true if you have this condition true right here, which is exactly what this other condition here. And then this chop goes away and the proof simplifies and you're able to make progress and go on with it. So, yeah, I was hoping to spend some more time on those examples, but I don't want to hold people for too long. Here's some links for doing some stuff, and some more links for resources. So any questions?
More questions from people, from the team, from outside, guests? Do you have questions? Thank you very much.
Oh, wait, sorry, I totally spaced how to let the one thing I wanted to get to here. The reason I picked this example is because you have to add the lemma to get the simplification to go through, right? And there's no real world proof where you're not going to have to add lemmas, right? And that's why in the presentation I had that extra argument that said -- requires, and then this file name lemmas.k -- imports demo lemmas. And this is how you add lemmas in K, is you make a new rule that's called a simplification rule. And you basically are just asserting that this is true to the prover and that it can do this anytime it sees this expression, it can simplify it to this expression. And so that enabled this chop to be simplified out and the proof to make progress. So I just wanted to go over that because you can't make progress with a K proof without adding lemmas in most cases.
Great. Are there more questions? Thank you very much, Everett. Thank you very much.